Year 12, and welcome to my 27th attempt at doing a video, an introduction to simple harmonic motion. Now, objects that undergo simple harmonic motion are things like swings, okay, an oscillation, moving backwards and forwards, just moving to and fro, okay, and a swing is probably a very specific example of a pendulum. And there we've got one oscillating backwards and forwards there. Okay, we'll look at these in much more details later on. We've also got a metronome. Okay, there we go, oscillating to and fro. Other things that do this are masses on springs. You pull the mass down and then let it oscillate naturally up and down. It's performing simple harmonic motion. And a vibrating string, particularly in a stationary wave. Okay, when every particle between those nodes just moves up and down, okay, they're performing simple harmonic motion, every one of those particles. So, we're going to look at what is simple harmonic motion. Well, it's one in which an oscillation where the acceleration of the object is directly proportional to its displacement from equilibrium, and is directed towards that equilibrium point at all times. Okay, so when we've got a harmonic oscillator, like a pendulum, if it's displaced to the left, its acceleration will be towards the right. If it's displaced towards the right, its acceleration is towards the left. Okay, so it's always in the opposite direction to its displacement and proportional to that displacement. So we've got our proportionality there, acceleration proportional to minus x, acceleration proportional to minus the displacement. And we can always turn a proportionality to an equation by introducing the constant. Now this constant is omega, or omega squared. Now we'll talk a lot more about this before, but we talk about omega as angular velocity in circular motion. Omega in simple harmonic motion is angular frequency. And in the next video, we'll really describe why we have that difference and the similarities between circular motion and simple harmonic motion, if I can get my activity to work. Now, if we look at our graph there in more detail, okay, we can see that when the displacement is negative at its furthest negative, we've got the maximum positive acceleration. That's just showing what that little equation proportionality was showing us. So if we take our pendulum again, now I'm going to displace it to my left. Now I know these cameras do funny things, they flip it and stuff, and you do selfies, everything's back to front and that. I think these work the same. So this is to my left, it might not be to your left, but anyway, displace it to my left. It's going to accelerate this way towards the equilibrium position. And it has its maximum acceleration when it's at its maximum displacement out here. As it goes, it's going to accelerate. It's going to reach its maximum speed as it passes the center, and then it's going to decelerate as it goes this way. Therefore, its acceleration is going to be in the opposite direction to what it's moving. So it's accelerated towards the left as it moves towards the right, up until it gets to its maximum displacement again. And then it'll start moving towards the left again, past the midpoint, and it'll carry on this way again. So at its extremes, acceleration is at its maximum. When it passes the midpoint, it's at maximum velocity, because beyond that it's going to slow down as it gets towards these bits. So where it changes direction, you get to zero velocity, where you change direction. Now, another thing just to mention when it comes to simple harmonic motion, wherever we've got an acceleration, we've got a force. So where we have maximum accelerations, we've also got maximum forces involved. So I'm just going to move my picture off there. There we go. So just be aware acceleration, high acceleration will mean higher forces as well. Now, other key terms we use in simple harmonic motion, I've talked about displacement, okay, what we move, left or right, velocity, how fast it's going in a particular direction, acceleration, time period, time it takes for one complete oscillation. So for things like a pendulum, if we're starting here, it's the time it takes to go all the way across and all the way back to there again. That would be one time period. Okay, frequency, the number of oscillations in 1 second. Okay, remember time period and frequency are the reciprocal of each other. So 1 divided by time period gives you frequency, 1 divided by frequency gives you time period. And then this new one, which we're going to talk about a lot more in the next video, this angular frequency, this omega. Okay, this relationship between circular motion and simple harmonic motion. Now, we are going to go on our final slide of this. So I just want to summarize what we've talked about there today. So simple harmonic motion occurs when an object oscillates about its midpoint. Its definition that an oscillation in which the acceleration is directly proportional to its displacement from equilibrium and is directed towards that equilibrium point at all times. It's directed towards that equilibrium point. So A is proportional to minus x, and when there's an acceleration, there is always a force doing it. There's always a force pulling these objects back to their equilibrium position. Okay, so that's just a quick short introduction to SHM. More to follow in the coming days.